Good morning, AOBI. This is Mr. Dunning. Stand by. I have news for you, and I have a math lesson for you. Okay, for news. Although the doors to AOBI are closed, school is still in session. Your math class is on YouTube, and you must do the work. That means that you have to watch the video, take notes, and get a copy of the notes to me. You can take a picture and email the picture to me as outlined in lesson 1. Or you can drop off hard copy at the front door. I'll take either one. But I want to talk to all you people who have done almost nothing. As of Thursday, at the end of the day, if I don't have your work, all of those lessons that did not get sent to me will permanently become zeros. Let me say this again. If I don't have your work by Thursday of this week, the unsubmitted work will go to a grade of 0. Now here's the reason. We're all stuck at home. We've got this quarantine. No stores are open. You've got no place to go. You've got nothing to do. You're like the rest of America. The only thing that you have to do is to get online, watch the lesson, take notes, and get the notes to me. There's no excuse. No excuse. The class can never go by too fast because it's on YouTube. That means you can pause the video and take great notes. No excuses. Thursday is the deadline for all past work. Now, the last piece of news that I have before we go to today's lesson is this. Lesson 12 was a quiz. And on Wednesday, I am going to go through the quiz and put up all the answers. If I don't have your quiz by the end of Tuesday, you can copy the correct ones into your notes. And I will gratuitously give you a 60% just for copying the correct answers into your notes. Today's lesson, you're going to learn sectors of circles and how to compute their size, and segments of circles and how to compute their size. Let's take a look at what a sector of a circle is and how you compute the size. This drawing here depicts a sector of a circle. In other words, a slice of the pizza pie or a slice of the cherry pie. It's bounded by 2 radii and the arc of the circle. A sector of the circle occupies some of the area of the circle, and the area that the sector occupies is easy to compute. The area of a sector of a circle is found by comparing this angle or this arc to 360. In this example, the area is 45 360ths of the circle. Now remember, the area of a circle is pi times the radius squared. So in this circle, the area would be pi times 10 squared, or 100 pi. The area of a circle is pi times the radius squared. In this circle, that would be pi times 10 squared, or 100 pi. We want 45/360ths of that. That expression would be the answer as to how big that sector is. 45/360ths of the area of the circle. In example 2, the angle here is 60, so we want to compare 60 to 360. The area of the circle is going to be pi times the radius squared in this circle. We left the radius 10. The area 100 pi. So we want 60 360ths of 100 pi. Now in this example, 60 over 360 can be reduced to 1/6. So a simplified version of the answer would be the area of the circle divided by 6, because 60 360ths is 1/6. In example 3, the angle here is 30. The area of this sector is going to be 30 360ths of the circle. The area of the whole circle is going to be pi times the radius 12 squared. So our formula for the area of the sector (30 360ths of 12 times 12 times pi. How about this point? You're saying, why did you write it this way? The answer is simple. Because when I divide 30 by 360, I get 1/12. My basic arithmetic tells me this 12 will divide into that 12, leaving the area of this sector 12 pi. A segment of a circle is this little skinny piece in here bounded by the arc of the circle and a chord joining where the two radii intersect the circle. Segment of a circle. We can find the area of that segment, but we need to use a sector and a triangle to do that. To find the area of this little piece here, this segment, what we need to do is look at the area of the sector, and we know how to compute that, and the area of this red triangle, and we should know how to compute that. So the area of the segment here is going to be the area of the sector minus the area of the red triangle. That's pretty straightforward, but sometimes we have to be careful when we look at the area of a triangle. Computing the area of this triangle is a lot easier than you might guess because the relationship will always be the same. Remember, this is an isosceles triangle, and both of those sides are radii. Now, the piece of that triangle that we care about is that green piece, the height. And that green piece is easy to compute. We need to use a trig function to do it, but it's still easy to compute. Let's look at a general case before we go to a specific example. Labeling this point A and this point B in circle O, the sine of angle A is going to be the side opposite. That will be the green piece, h, the height, divided by the hypotenuse. So in this picture, h can be found using the sine function of this angle. That will generally be true. R times the sine of A will give us the length of h. Now, how about half the base? Well, again, we're going to use a trig function. But this time it won't be sine. It will be the cosine of this angle. And the cosine of A the cosine of A, side adjacent, divided by the hypotenuse, will be half the base divided by the radius. Now we have a formula for half the base and the height. That's all we need to fill in this formula for the area of this triangle. When we plug in these relationships, half the base is r cosine A, and the height is r sine A. So we can always use trig to give us half the base times the height with this formula. In example 2, we have a circle, radius 10, and we'd like to find out the area of this segment. Well, the area of the segment is going to be the area of the sector, this slice of the pie, minus the area of the triangle here. And we can find both. The area of the whole circle is pi times the radius squared, or 100 pi. But we only have 1/4 of that. So the area of the sector is 1/4 of the area of the circle, or 25 pi. The area of the triangle. Well, we have a 45, 45, 90 triangle. The Pythagorean triple that we start with 1, 1, square root of 2. So the piece that we knew, 10, was the piece that should have been the square root of 2. So what did we do to the square root of 2? We multiplied it by n. And the n that gives us a 10 over here is 10 over radical 2. That's our multiplier. So the piece that's 1 is actually 10 over radical 2. Piece that's 1, again, 10 over radical 2. So both the green piece here and this piece here are 10 over radical 2. That is half the base, by the way. Half the base is 10 over radical 2. And now we can put that in. Half the base, 10 over radical 2, times the height, 10 over radical 2. That's going to be 100 over 2, or 50. So the area of our segment will be 25 pi minus 50. The area of our segment here will be the area of the sector, 25 pi, minus the area of the triangle, 50. This has been pretty complex. We'll go through some more examples tomorrow. Meanwhile, you've been a great audience. I hope you have a wonderful day. We'll see you all tomorrow with some more examples.